Continuity Part 3. We're going to talk in Part 3 about compositions. If G is continuous at A and F is continuous at G of A, then the composition f of G of X is continuous at A. That's a little hard to understand, but what I'm going to do is I'm going to try to help you see where a composition is continuous. Here's the steps you want to take. You want to look at the inside function and find all the values allowed by the inside function. Then, of those values, which of those result in an allowed value for f? Let's do an example. This is a composition of secant and radical. For what open intervals going from 0 to 2 pi is the square root of secant x continuous? The first thing you ask is where is the inside function secant? Where is secant continuous? Then, which of those values result in an allowed value for the radical? So step 1, find all values between 0 and 2 pi allowed by secant. Secant is 1 over cosine. So all the values between 0 and 2 pi that are allowed by secant, all the values are the open interval from 0 to pi over 2, from pi over 2 to 3 pi over 2, and from 3 pi over 2 to 2 pi. So there are 3 open intervals on which secant is continuous. Secant is continuous from 0 to pi over 2. It's also continuous from pi over 2 to 3 pi over 2. It's also continuous from 3 pi over 2 to 2 pi. It's not defined for pi over 2. It's not defined for 3 pi over 2. Now, which of those values are allowed by the radicand? So, for which of these values will you get something that can go under the radical? Well, from 0 to pi over 2, secant is positive. So I can take the square root of secant. But from pi over 2 to 3 pi over 2, secant is negative, and you can't take the square root of a negative value. So the interval pi over 2 to 3 pi over 2 is not allowed. Then, from 3 pi over 2 to 2 pi, there secant again is positive, and you can take the square root of a positive number. So the intervals on which the square root of secant of x is continuous is the interval from 0 to pi over 2, and then from 3 pi over 2 to 2 pi. And in fact, right here I have a graph of what the square root of secant looks like. One remaining issue to discuss is the intermediate value theorem. Suppose f is continuous on the closed interval from a to b, and suppose L is a number between f of a and f of b. Then there is at least one number in C between a and b satisfying f of c equals L. So if you have a function that's continuous from a to b, and L is between f of a and f of b, then there has to be a number c between a and b where f reaches that height of L. Let's look at an example. This function is continuous on the closed interval from 1 to 4. Show that there exists a point on the open interval from 1 to 4 such that f of c equals 3. Well, we're just going to use the rules for using the intermediate value theorem. So it's continuous on a closed interval. What we need to do is find the value of the endpoints. F of 1, what is that? And f of 4, what is that? F of 1 is equal to 2, and f of 4 is equal to 5.6. So if I were to do a graph of this, I don't know much about my function, but I know at 1 it gets a height of 2, and at 4 it gets a height of 5.6. The intermediate value theorem says that sometime between 1 and 4 the function has to reach a height of 3. Okay, so we've shown, because 3 is between 2 and 5, we've shown that there has to be a point between 1 and 4 where the function reaches the height of 3. Well, where is that point? The intermediate value theorem is just what's called an existence theorem. It doesn't tell you how to find a point. It only tells you that the point exists. So suppose we want to find the point between 1 and 4 where the function takes on the height of 3. Where does that occur? Between 1 and 4. Between 1 and 4, where does the function take on a height of 3? Well, that's really just an algebra problem. So we're going to take the square root and set it equal to 3. And it's just solve for x. We square both sides. So take the square of both sides. And then we've got a quadratic on the left-hand side. So we subtract 9 from both sides. And then on the left-hand side, if we can, we factor it. And so there are two places where this equation is solved, and that is at x equals -3/2 and at x equals 2. Now the point 2 is between 1 and 4. So our point 2 is where our function takes on the value of 3. So f of 2 equals 3, and that's the point that satisfies the intermediate value theorem. Take care, and I will see you later.